In this tutorial, we will explore the design of a radio frequency low-noise amplifier, LNA, using advanced design system software. We will extract key performance parameters and examine strategies to enhance LNA performance. A low-noise amplifier, LNA, is an RF amplifier designed to boost weak signals while introducing minimal noise. It is widely used in wireless communication, satellite systems, and radio astronomy to improve the signal-to-noise ratio (SNR) in receiver circuits. Why is an LNA important? An LNA plays a crucial role in enhancing signal strength while keeping noise levels low, improving receiver sensitivity, minimize the signal loss. Several critical parameters must be considered when designing an LNA. Gain, the ratio of output power to input power, representing the amplification strength. Noise figure indicates how much noise the amplifier introduces into the signal. A lower noise figure is preferable. Stability ensures the LNA operates without unwanted oscillations under various conditions. Linearity, measured by IP3, third-order intercept point, and P1 dB, 1 dB compression point. IP3 represents nonlinearity and distortion. Higher values indicate better linearity. P1 dB, the power level where gain drops by 1 dB due to saturation, indicating power handling capability. Among these parameters, the noise figure is particularly critical. It quantifies the noise introduced by the LNA compared to an ideal noiseless amplifier. The LNA's gain and noise figure significantly impact the overall system's noise performance. The total noise figure of a receiver is determined by contributions from all stages, but the LNA's characteristics are the most influential. In this tutorial, we will design an LNA using advanced design system and analyze all essential performance parameters. Let's get started. In this design, we will use the ATF13284 transistor. However, before proceeding with the design, we must first determine the bias point for this transistor, open an ADS schematic, and import the transistor model. Define voltage sources at the gate and drain terminals to establish the bias point. Use the DC analyzer to extract the gate voltage, drain voltage, and drain current for biasing. Based on the datasheet information, we will set the drain voltage VD to 2.5 V. Define the gate voltage VG as a variable. Introduce a sweep parameter for VG to analyze its effect on the transistor's operation. Place a probe at the drain terminal to measure the drain current. By sweeping different gate voltage values, we will plot the drain current ID as a function of gate voltage. For LNA design, operating in Class A is preferable since high efficiency is not a priority in this application. A gate voltage of approximately 0.1 V to 0.2 V results in a drain current of around 40 milliamperes, making it a suitable operating point for this LNA. In this step, we will analyze the stability of our LNA circuit to determine whether it will oscillate under specific frequencies and conditions. To do this, we need to reintroduce the transistor model and apply the previously determined bias point. Include DC feed and DC block components in the circuit. Evaluate the stability factor, mu factor, to ensure it remains greater than 1 over the desired frequency range. For this design, we are targeting an operating frequency of 1.8 GHz. Since the LNA operates in the lower power range, we can use S parameters as a small signal analysis tool to assess key design parameters. To comply with IEEE standards, we must set the simulation temperature to 16.85 degrees Celsius. This can be done by selecting the appropriate option from the simulation palette in ADS. Upon simulation, we observe that at 1.8 GHz, the mu factor is less than 1, indicating potential instability. Additionally, even when extending the frequency range, the mu factor remains below 1, confirming the need for stability enhancement. To analyze the noise performance, we will use the S-parameter analyzer to extract noise figure, the amount of noise added by the amplifier, minimum noise figure, the lowest achievable noise figure for the transistor, S21 parameter, the gain achievable under 50 ohm source, and load conditions. These parameters give us insight into the amplifier's noise contribution and performance before impedance matching. To improve the circuit stability, we can add a shunt series RC circuit, selecting appropriate component values to increase the mu factor above 1 at the desired frequency. If global stability is required across all frequencies, further tuning is necessary. An additional series resistor at the drain terminal can help improve stability, but we must avoid placing a resistor at the gate terminal, as it would degrade the noise figure. Even if the mu factor remains below 1, we can still proceed with the design by implementing a stability circuit at the input and output. However, for unconditional stability across all impedance conditions, additional elements must be added to keep mu1 across the entire frequency range. That be why carefully selecting component values, we can optimize the noise figure, gain, and stability for the best performance. To visualize the impact of our stability improvements, we can plot the source and load stability circles on a Smith chart, run a simulation to determine impedance regions before and after stability enhancements. Observe that without stability elements, impedance selection is limited. After adding stability components, the stability circles move outside the Smith chart, allowing greater flexibility in impedance selection. By fine-tuning these components, we can achieve a stable LNA design that meets the required performance metrics. After verifying circuit stability, the next step is to select the best input and output impedances for the transistor to design a matching network and complete the LNA circuit. To do this, we need to analyze gain circles and noise circles, which provide insight into transistor behavior and help us make informed impedance choices. We start by copying the schematic from the previous stability analysis. Then, we add the required simulator components from the palette to generate gain and noise circles. Gain circles represent regions of constant transducer gain on a Smith chart. Noise circles indicate regions of constant noise figure. In LNA design, these are two critical parameters that must be balanced. We choose a method to plot the gain circles, selecting 8 circles with a 0.5 dB increment between them. Similarly, we plot 8 noise circles, each spaced 0.2 dB apart. With the stability circuit, gain circles, and noise circles plotted on the Smith chart, we can determine the best impedance points for optimal performance. To achieve the minimum noise figure, the best choice is gamma optimum, which corresponds to the optimum source impedance for noise performance. However, choosing this point might not yield the best return loss at the input. If we prioritize noise performance, we select gamma optimum. If we aim for better impedance matching, we may compromise slightly on noise to improve. Return loss. A balanced choice between gain and noise figure can also be considered. Unlike the input impedance, the output matching follows a straightforward approach. The impedance seen from S22 is conjugate matched to 50 ohms, ensuring maximum power transfer. No trade-offs are required for noise figure in the output matching stage. Since the circuit is already confirmed to be unconditionally stable, we can select any impedance within the stability region of the Smith chart. If we select the best gain impedance, we may not achieve the best noise performance. In this design, we prioritize minimum noise figure by selecting gamma optimum and evaluating its impact on S11. While this choice ensures optimal noise performance, it might slightly affect input reflection coefficient performance. After selecting the input and output impedances from the previous step, we now design the impedance matching networks to ensure maximum power transfer and minimal reflections. Advanced Design System provides tools to facilitate this process. We access the Smith chart utility from the ADS palette and open the matching tool window. By setting the desired frequency and input-output impedance values, the tool calculates the necessary transmission line parameters. Adjusting the impedance dynamically affects the required length of matching elements. A two-section cascaded microstrip line can be used to match the input impedance to 50 ohms. The impedance and length can be adjusted based on design constraints, such as circuit size and fabrication limitations. Once the matching network is designed, it can be automatically generated within the Smith chart tool. Transition from ideal transmission lines to practical microstrip lines, we define the substrate. In this design, we use RO4003 as the substrate material. The line calc tool in ADS helps compute the width and length of real microstrip lines based on electrical parameters. The required information is entered, and the tool calculates the physical dimensions of the transmission lines. A quarter wavelength transmission line with a capacitor-loaded ground is used to provide DC power without interfering with the RF section. This isolates the DC bias from the RF signal path. A series capacitor is introduced to block DC current. A 50 ohms microstrip line connects the capacitor to the input terminal, ensuring minimal impact on circuit performance. By deactivating ports and adding pins, the design can be converted into a schematic symbol. This symbol can then be used in the final schematic, making the design modular and reusable. After designing the input matching network, the next step is to design the output matching network. The process is similar to the input matching design, but is generally less challenging since we only need to match the conjugate impedance seen from port 2 to 50 ohms. The Smith chart utility in ADS is used to design the output matching network. The frequency and impedance values are set to match the output impedance to 50 ohms. By adjusting the impedance, the associated transmission line length changes dynamically. Similar to the input matching, A two-section cascaded microstrip line is often sufficient for optimal performance. ADS automatically generates a matching network with ideal transmission lines. To convert it to a practical design, we follow the same process used for the input matching network. Once both input and output matching networks are designed, they are integrated into the main circuit. The stability components added in the earlier step must be retained to ensure stable operation. The DC bias sources are applied to the specific pins defined for the input and output. Since we are not analyzing large signal behavior, an S-parameter simulation is used to evaluate circuit performance. The desired frequency range is set in the S-parameter analyzer. Proper terminal connections are necessary to obtain accurate results. A small tuning of the input and output matching networks is necessary to achieve the desired frequency response. Although the detailed tuning process is not shown here, it can be performed manually in ADS to optimize circuit performance. The output matching network performs well, ensuring proper impedance transformation at the output. The gain and noise figure are within an acceptable range. The noise figure is approximately 1.3 dB. The gain is measured to be between 13 and 14 dB. As expected, input reflection coefficient is not optimal because we selected SOP for minimum noise figure. This confirms the trade-off between noise figure, minimized when choosing SOP, gain, and input reflection coefficient. To modify the performance, we can return to the gain and noise circles and select a different input impedance that balances the trade-offs. The stability factor mu is greater than 1 over the entire frequency range, confirming that the circuit remains unconditionally stable. In the previous design, we selected gamma opt as the input impedance to achieve the minimum noise figure. However, this choice degraded the gain and input reflection coefficient. The optimal gain point is far from the minimum noise figure point on the Smith chart. To balance the trade-offs, we have chosen a new compromise impedance that slightly increases the noise figure but improves gain and input return loss. The output matching remains unchanged as it is already optimized. The new input impedance is matched to 50 ohms using Smith chart tools and ADS. We implemented the new impedance matching network and updated the input model. Noise figure degraded to 2.2 dB at 1.8 GHz. Gain increased to 17 dB, previously 13 dB. Input reflection coefficient improved, enhancing impedance matching. Stability factor mu remains greater than 1, confirming the circuit is still unconditionally stable. If you are interested to these kind of videos, subscribe to the channel or like the video. Thanks for watching.